So a rectified linear unit, it is also called as a ReLU. ReLU. So what is this ReLU? It's an activation function. Activation function. So what are activation functions? We saw that we have neuron here. There are inputs coming to this neuron, x1, x2, x3, and we have weights here. So in this neuron, what we do here is we do this uh, sum of the products of weights and inputs. So W1 x1 plus W2 x2 plus W3 x3, and on this sum we apply this function here. So this function is nothing but activation function, and result of applying this activation function on this sum is giving us the output of this neuron. So O is equal to f of this. So let us call this as Z. Let me call this as Z. So O is equal to f of Z. So Z is nothing but this sum, right? So this f is nothing but activation functions. Activation function, and we saw that there are many activation functions. We primarily discussed two of those. One is called sigmoid, the other one is called as tanh. These were the two most popular activation functions in 90s, 80s, and early 2000. But they were causing the problem called as vanishing gradient problem. Vanishing gradient problem. What is this problem in brief? So uh, when we're doing backpropagation phase, during that we're computing a lot of derivatives and multiplying those derivatives. So derivatives of activation function we're computing. So for example, in order to compute the derivative of loss with respect to some weight, we are doing do derivative of loss with respect to some output. Let's say O31, then derivative of O31 with respect to O21, then derivative of O21 with respect to O11, and O11 with respect to, let's say, W. For just an example here. So these derivatives are nothing but derivatives of activation functions, because though this is O, this O output is coming from this activation function. That means here we are ultimately taking derivative of this activation function. So we are multiplying derivatives of activation functions, and those activation functions were primarily sigmoid or tanh. And we saw that the derivatives of sigmoid or tanh were fractions. They were less than 1. So the values like zero point 0.2, zero point 0.1, 0.05. So we're multiplying many such values, and as a result of that, we're getting this derivative as a very small value like 0.001, etc. Now, by using this value, when we're updating the weight by using the formula W new is equal to W old minus eta times derivative of loss with respect to W old. So this term was this one, right? So we're putting this term here, and as a result of that, this W new was very similar to W old. It was very similar to W old. That means this W new was not getting updated, weights were not getting updated. That means we're not able to train neural networks. So this we saw only with this we saw with a neural network of two layers. Imagine if there are many layers, this term may be very small, and the weights will not update at all. So that's why people were not able to train deep neural network because of this activation functions only. Sorry. And such a problem is called as vanishing gradient problem, which was causing the convergence to solution very slow. The convergence to solution was very slow because of this vanishing gradient problem, which was there because of these activation functions. Now, with the advent of tanh, with the advent of this ReLU, let's see how we can handle this vanishing gradient problem. So let us first discuss what is the ReLU, right? So ReLU, if we apply, as I said, This ReLU is nothing but activation function, so it's a function. So let me, so f of z, this f is nothing but activation function, but this time this is, let's say, ReLU. F ReLU of z is equal to, when we apply this ReLU on z, what we get? We get only two values. There are only two possibilities, either 0 or z, right? When we apply this ReLU on z, what is z? Z is nothing but this sum, right? When we apply ReLU on this sum or z, we get only two values, so either 0 or 1. When we'll get a 0? When z is negative. And when we'll get a value z? When negative or 0. That means when z is less than equal to 0, we get f ReLU of z as 0, and when z is positive, we get f ReLU of z as z itself, right? So that is the result of ReLU when we apply on z. Now you see, if we plot the graph of this, if I plot the graph of this, the graph will look like this. So if I plot a graph, so if this is z here and this is ReLU, f ReLU, f of z ReLU, right? So when z is positive, we saw that, let's say z is +1, +2, +3, and this f ReLU is this +1, +2, right? So when z is positive, let's say z is 1, so that time what we get? F ReLU will also be 1, so we get this point, right? When z is 2, f ReLU is also 2, right? That means whatever value of z, same value of f ReLU. So if I plot this line, this will be exactly a line making 45-degree angle with this axis as well as this axis. But when z is negative or 0, we'll get f ReLU as 0. That means this kind of line we'll get here. When z is negative, we'll get f ReLU as 0. So that is a plot of f ReLU. Now, if we compute the derivative of this, derivative of f ReLU, right, with respect to z is equal to, if I take derivative of this, derivative of 0 will be 0. And if I take the derivative of z with respect to z is 1. Right? Or on the contrary, if we, I mean not on contrary, but if we see here, if we take the derivative of this line, derivative will be exactly 1, right? 1. So, sorry, sorry. So, derivative of, this is the derivative of ReLU, and this 0 is for negative z, and this 1 is for positive z, right? So if I plot the derivative uh, graph, it will look like this. So so the graph of this will look like this. So the derivative of uh, positive z will be 1, like this, and derivative of negative z will be 0, like this, right? So this is the positive z, this is negative z, and this is f derivative of f of z ReLU with respect to z, right? So now the point to note here is, computing this ReLU of z and computing a derivative of the ReLU of z is very simple. You see, the ReLU of z is either 0 or z, right? And derivative of ReLU is either 0 or 1, right? This is for uh, z less than 0, z greater than 0, right? So computing ReLU and derivative is very, very simple, and that's one of the most important reason, right? What is that? The simplicity of calculation, or ace of calculation was one of the most important reason, or one of the reason which made ReLU very popular, and ReLU today is the most popular activation function used, right? So because of its simplicity of calculation. Now let's see how ReLU can help us to get rid of the problem of vanishing gradient. So we saw that in the backpropagation stage of the training of a neural network, we multiply a lot of derivatives, right? In order to get derivative of loss with respect to weight, we multiply a lot of derivatives here, lot of derivatives. So when this derivative is of very small, we get the very smaller value of this derivative, and because of that we will not be able to update the weight. But now in case of ReLU, these derivatives can be either they can be either 0 or 1, 0 or 1, right? So these are derivatives here, they can be either 0 or 1. Now, when this will be 0, this entire term will become 0. So derivative of this loss with respect to it becomes 0. So that will cause another problem called as dead activation. So we'll discuss that problem later, but that's very rare case when dead activation occurs, and how to handle that problem. We'll see that. But for now, just let's consider these are ones. These are ones, right? So when these are ones, we have 1 into some term here. So we are not having a fractional term or smaller value here. We are not having a very smaller value here, right? And because of that, we will not have the vanishing gradient problem, because this derivative is not very, very small term. So we'll be able to update the weights, right, by using the formula W nu is equal to W old minus eta times the derivative of loss. Right? So that's how the ReLU helps to get rid of the vanishing gradient problem, and because of that, that we are able to converge to the solution very faster. Now, if I plot according to a paper in which this ReLU was published first, uh, the plot, if I show the plot in that paper, I'll directly show you the plot. So they compared the convergence of tan H and the convergence of ReLU. So if this was kind of graph shown for tan H, right? And this was the kind of graph shown for ReLU. Right? Now, what is this? This is epochs here, epochs, and this is the graph of tan H, and this is the graph of ReLU. Right? Now, you see, the tan H was converging to the solution, very slowly, right? Let's say if this was 100 epoch, just for example, and this is, let's say, 10 epochs. That means ReLU was converging to the solution very fast, and whereas tan H was converging very slow, right? So convergence to the solution is very faster in case of ReLU. And why is that? Because we don't have this vanishing gradient problem in case of ReLU. Okay, so now let's discuss the problem of ReLU. The problem of ReLU is dead activation. Dead activation means when one of the derivative becomes 0, right? And when can the derivative become 0? The derivative can become 0 when we have this negative value of z. The derivative is 0 for the negative value of z, for negative z. And now when can z be negative? Now, what is Z? In the first place, Z is nothing but multiplication of weights and inputs, right? Now, the possibility of Z becoming 0 is only when these W's are very large negative numbers. These W's are very large negative numbers. So, if we take care of initializing weights and see that weights are not very large number, so that time this Z may not become negative, right? And now if Z becomes negative, let's see how to handle that problem, right? So let's say somehow Z become negative, so how to handle this problem? This problem can be handled by using this technique. Let's say we have this ReLU here. So this is So this is the graph of ReLU. So this is Z and negative Z, and this is F ReLU of Z, right? Now, if what will we do? We will give a small value to this rather than having this Z or F ReLU of Z as 0 when Z is negative. We'll give it a small value like this, right? That means if I modify this F ReLU of Z is equal to some small value A into Z, and this will be Z, right? So this will be when Z is negative and less than equal to 0, and this will be when Z is positive, right? So we are giving this small value here, this small value here, right? So this A can be a very small value like 0.01. Let's say A is very small value like 0.01. So we are giving when Z is negative, we are making this F ReLU as AZ. That means F ReLU is a smaller value compared to Z, because this A is small. This A is small, because of that this value is becoming smaller. When Z is negative, we'll have this value, and when Z is positive, so we'll have F ReLU as Z itself. And what will happen if I take the derivative of this? If we take, so if I derive this, if I take derivative of this, so this will be derivative of this will be A, and derivative of this will be 1, right? So that means the derivative of F ReLU of Z with respect to Z will be, now in this case we are talking about, so this will be A and this will be Z. Sorry, this will be 1, right? So for Z greater than 0, Z less than 0, right? So now you see, because of this, what will happen, right? So because of this, what will happen is, let's say we are multiplying lots of derivatives, right? So now you see this derivative term is never 0. It's never 0. It's either 1 or A. It's either 1 or A. That means this multiplication of derivatives will never become 0. It will never become 0, right? It will never become 0 because we don't have a 0 term here. So that's why we will not have a dead activation problem. Will not have a dead activation problem. Right? So such a ReLU in which we are giving this smaller value to ReLU, such a ReLU is called as leaky ReLU. And leaky ReLUs are used in order to handle this dead activation problem which we are getting in ReLU, right? So that is a ReLU activation function. So what we saw in ReLU, the value of F ReLU of Z is equal to max of 0 comma Z. So it will be 0 for Z less than equal to 0, and it will be Z for Z greater than 0. So, and the derivative of this will be either 0 or 1 in case of derivative is either 0 or 1 in case of the main ReLU, that means the ReLU which is not leaky ReLU, right? So the derivative will be either 0 or 1. So because of this, because of ReLU, we are getting rid of the problem of vanishing gradient. And when we don't have vanishing gradient problem, we have faster convergence, right? And that's one very important point. And that's why this ReLU become very popular. And because of ReLU, deep neural network themselves became very popular. Right? So ReLUs are helping us to get rid of this problem. Then the second thing is ReLU are very simple. They are very easy to compute. The ReLU and the derivatives of ReLU. It's very simple, very easy to compute. Right? Simplicity or ace of calculation. Simplicity or ace of calculation. And these were the two important plus points of ReLU. The other what is the drawback of ReLU? The drawback of ReLU is we are getting dead activation. Dead activation. So how do we handle this dead activation? By using leaky ReLUs. Leaky ReLUs, or by using we can use we are running into this problem of dead activation because of the negative values of Z. The negative values of Z we're getting because of large negative weights. So if we handle the initialization of the weights, we can get rid of this problem, or we can go for leaky ReLU. So these ReLUs are also sometimes called as rectifier, only rectifiers. Rectifier. So that's it for this ReLU activation function. So we'll meet in the next video.